Hey y'all, so this was the other question that we had in class, which dealt with a pendulum. We actually started looking at it in class. We come up with a couple ideas of how to deal with it. We've got a pendulum with essentially a massless string here with a length of 1 meter. We've got the mass, essentially all the mass is hanging on the end, and we're going to release it from an angle of 10 degrees, and it's going to swing down like a normal pendulum. And what we want to do is we want to try to find the speed or the velocity of the pendulum at that lowest point, right? Now in class we talked about a couple of different ways to accomplish this. Somebody said, well, maybe we can use centripetal force. And in fact, we did see a couple of situations when we were looking at centripetal force where somebody was hanging on a string or on a rope like a pendulum, and they were swinging and they hit something and the radius of your pendulum changed, and we were able to use some centripetal force there. So it's a good possibility. We also had the idea of talking about the conservation of energy, the change of energy equals the work, the idea that we have energy conserved, and that's feasible as well. Remember we had the mass that we held in front of our face, and as we let it go, it swung over and it came back, and we know that for a pendulum, that energy is conserved, right? The only forces are gravity, so if we consider the pendulum Earth system, then gravity is an internal force. It's considered in that UG, that gravitational potential energy, and the string, of course, is always perpendicular to the motion, so that force doesn't do work. So we do know that energy is conserved for a pendulum. So let's look at those two solutions. I know there is a right answer here, but I'd like for you to think about why does one of these work and the other one doesn't, all right? So if we were to consider first centripetal force, this was the first one mentioned in class, so we're going to look at that one. So if we look at centripetal force, okay, what we would be interested in is the velocity at this point. So we really want to be able to deal with the centripetal force at that point, right? Now, in order to do that, we need to know what are the forces acting on it. Well, we've got the force of gravity pulling down, and we've got the tension pulling up. Now at that point, what do we know about those two forces? Are they the same? Is one bigger than the other? Well, hopefully you recognize that the tension has to be bigger than the force of gravity. We have a couple of ways to justify that. The first one is, after this point, what happens to it? Does it keep going in a straight line? No. If the forces were balanced, the ball would continue to go in a straight line, right? The fact that it is not, the fact that it is swinging up from there, must mean that it is accelerating upwards, therefore the tension must be larger than the force of gravity. The second way to look at that is recognize that if we are thinking about centripetal force, centripetal motion, in order for it to go in a circle, the net force needs to be towards the center of the circle, which is up. So once again, the tension must be larger than the force of gravity. So we've got a couple of ways there that will help us understand the tension's got to be larger than the force of gravity. So the centripetal force, which is equal to mv squared over r. Again, remember that in the formula packet, it doesn't give you centripetal force, it gives you centripetal acceleration, which is the v squared over r, but we also know that force equals ma. Actually, sum of the forces equals ma. So if my centripetal force, acceleration centripetal, is v squared over r, then mv squared over r would be our centripetal force, right? So centripetal force equals mv squared over r. The centripetal force is the combination of all the radial forces, which would be tension and the force of gravity. So I'm going to go tension minus the force of gravity equals mv squared over r, right? We do know the radius. The radius is 1, so I'm going to try to start putting in some numbers there. I got 1. I don't know the mass. That's not given to me, so that's a variable. I don't know the speed. That's actually what I'm trying to find there, is the speed. I can't find the force of gravity without the mass, and so the force of gravity, I guess I could put mg there. Maybe that'll be helpful to recognize the m. Maybe it'll cancel out eventually. And then I've got the tension, which of course the tension at this point is unknown. What I recognize as I start to look at this is I really don't have much information at all, right? I can't get rid of mass, because if I divide by mass here, I got to divide by mass here, and I have to divide by mass here, which means I'm going to have T over m, which I don't know if that's any better than having the m's there right now. right? I guess I'd have 1m instead of 2, but really I still have m. I still have that variable. I don't know what t is. I don't know what v is. There's just too many variables here, right? I can't really answer this question in this format. So at this point we say, unless I can get really creative, this is probably not the way to go, all right? So let's have a look at conservation of energy, all right? That's the other option. Now, we may get to a point here where we say, I don't know what to do, and we may have to then decide between the two options. But let's go ahead and give conservation of energy a try. I'll give you a hint. 9 times out of 10, maybe 9.5 times out of 10, if it's a pendulum, you are probably going to be using conservation of energy. One of the only exceptions I can think of is the one in our homework packet where the radius was changing, but we had other information there, right? We knew the mass of the pendulum. We knew a lot more things in that situation, all right? Most of the time, you're going to be doing conservation of energy. Now, we know that the change in energy is 0. We also talked about the idea that that means that the initial energy must be equal to the final energy, right? Energy is being conserved here. If we define my lowest point, my lowest important point, right? This is an important point, and my starting point is an important point. That's going to be my initial and my final. So I'm going to define that as height equals 0, right? So at my initial point here, I'm starting at rest, but I do have gravitational potential energy, right? No kinetic energy because the speed is 0. As it drops, that gravitational potential energy is going to turn into kinetic energy, so that by the time it gets down here, my kinetic energy is going to be all that I have. So it's all kinetic there, and I'm at a height of 0, so gravitational potential equals 0. So in this situation, I do end up with UG, which is mgh initial, which will equal 1/2 mv squared final. Okay? Now, what I notice is in this situation, the masses are going to cancel out, which leaves me just with g h naught equals 1/2 vf squared. And that, again, is what I'm solving for. I have the g, the 1/2 is a constant. So really, in this situation, all I need is the initial height. Okay? So looking at the two things, right, the two possible paths, this one looks significantly simpler than this one does. All right? Now, simpler does not mean easy, right? Because I still do need to find the initial height. How high is it? And that's going to need some math. All right? So let's talk about how we get that initial height. Looking at my diagram here, I know that it starts at an angle of 10 degrees. Okay? I need to find out how high is it. Okay? How high is it from that h equals 0? That's the goal. Now, you'll notice that if I do this, I have created a right triangle. This is definitely vertical because it's hanging down. This is definitely horizontal because it's parallel to my height 0, which is flat, right? So those two are definitely perpendicular. Sometimes I see students try to make a right angle here. That doesn't work. Number one, we already know that the radius of a circle is perpendicular to the tangent to the circle, which means that if I want a right angle here, that it's going to be outside of my curve, not inside the curve. I need a right angle because I can do trig, I can do math pretty easily with a right angle. Okay? So notice that with this right angle, this triangle right here, I have the hypotenuse, I have an angle, I can solve for this side. Now when I solve for that side, it's only going to give me the distance from the pivot point down to here, which is where the ball started at, where the pendulum started at. Now hopefully you're recognizing, Mr. Bobbitt, I know that if you have the total pendulum, which is a length of 1, if I find this, then I should be able to subtract that and get the height the initial height of my pendulum. So that's what we're going to do. Okay, so here I've got, this is the opposite side, I need the adjacent and the hypotenuse. So that would be cosine. Cosine of theta equals the adjacent over the hypotenuse. Okay, so that'll be cosine of 10 equals the adjacent, which is x, over the hypotenuse, which is 1. And so that'll be 1 times cosine of 10. And now, again, I'm going to pull out my fancy calculator, which actually I don't even know if I know how to do a cosine on here. Oh, look at that, I do. All right, so I got cosine of 10. I got 0.9848077. I'm going to write down a couple of digits just because it's a pretty small number. So I got 0.9848. I'm not going to keep all these digits when I get to my final answer, right? I am going to look at significant figures, which is probably, I guess, in this case, just 1. But for now, I'm going to go ahead and keep that 0.9848. Okay? So now I can take my full meter and subtract that 0.9848. And I get that the initial height there is 0.0152 in order to have the same number of digits as I have there. Not the same number of significant figures, but I only had 4 digits there. So 1, 2, 3, 4 to the same place. So that's my initial height. Okay? So now, now that we've done all that math, we can take that and we can put it in for our height. And so we're going to have the g, which was 9.8. We're going to multiply it by the height that we just found, that's 0.0152, which is in meters, right? I was careful to make sure that everything was in meters, equals 1/2 v final squared. So let's do the math. So I'm going to take that, I'm going to multiply it by 9.8. Okay, and that gives me 0.14888. And then I'm going to multiply by 2 or divide by 1/2. And that gives me 0.29776. Okay, and so now I end up with that 0.2978, because I'm going to just round that up, equals final velocity squared. So now I need to take the square root of that. 0.2978, and I get that my final velocity equals 0.54 meters per second. We did recognize that this was one significant figure, so I suppose my final answer should be 0.5 meters per second. There we go. Now you may say, but Mr. Bauer, that's not very fast. Well, first off, it's not that slow either. That's 0.5 meter a second, right? That's decent speed, right? Secondly, this pendulum was only brought up to a 10-degree angle, right? 10 degrees. That's 1/9 of a 90-degree angle. So that's like it was hanging here, and 10 degrees is like right there, right? And so I pull that pendulum up to here. And by the time I release it, by the time it gets to the bottom, it's already traveling at 0.5 meter a second. That's actually fairly significant, right? So it's not quite as slow as you might think. Yeah, it's not a race car, but it's a pendulum, right? Okay, so get over it. Anyway, there you go. That's the idea. Recognize that we looked at both possibilities. Sometimes you have to do this, right? But as you practice more and more, this is one of the reasons why we have so many practice problems, why we have so many questions inside of AP Classroom, is because the more questions that you work, the easier it will be for you to look at a problem and say, well, I could use this, or I could use this, or I could use this, but really the best one I think is going to be this one. We're going to be wrong sometimes, and that's okay. I'm wrong sometimes too. You guys have noticed it in class. Sometimes I make mistakes, but most of the time we will be able to make a good choice from the get-go. All right? So I hope that was helpful. We were able to solve for the answer. We also were able to talk about some other things, like how we knew that the forces were not equal at the bottom of a swinging pendulum. It's different if the pendulum is just hanging at rest, right? If it's hanging at rest, it's at rest and staying at rest, therefore the two are equal. But we recognize that as it's swinging, those forces are not equal. Okay, we recognize that, yeah, we have used centripetal force for a pendulum in the past, but depending on the information that we have, that may or may not be the way to go. All right? So hopefully that was helpful, and we'll see you next time.